Okay. Sounds good. I just started recording. So let's see. Sorry. Okay. So there are like three main things I think I want to try and cover today, and they sort of stem off of what we did yesterday. I don't know if you were here. The three different topics are like the intermediate value theorem, which is sort of just like an idea or concept that I can just go over, and it's pretty self-explanatory. So hopefully it shouldn't be too bad. And there's also like just general like rules of differentiability, which sort of stems off from continuity, which we did yesterday. And then also there's like one-sided limits for like actual functions. If you remember me talking a bit about that. So I think I'm going to go over those one-sided limits like first, just because I think that's kind of important, right? Okay. So I'm just gonna like write down like an example of what one of these like look like. Does that sound good with you guys, or do you have any like specific concepts that you guys want me to go over, or like sort of review, or any questions that you've like run into that you think might be a good idea to like go over? Like this is all for you guys, so I don't have to do what I do. What I planned on doing. Sort of. It's cool if not. Sounds good. Okay. Cool. All right, so there's this limit that I want to take a look at. I think it's this. Can you see that okay? Yeah. Okay, I gotta double check something just to make sure that it's the right one. Sorry. Okay. Yeah, okay, cool. So when you first look at this, you might, if you try to plug it in like normal, you kind of like plug in, so like, okay, plugging in. You get 1 over 1 minus 1, 1 over 0, right? And then you can't do that. That makes sense. So that's, since it's undefined, that doesn't work out, right? It doesn't really look like it. So there's not like a limit number that is really going to, at least from the right side, right? And same thing from the left, like it's not specifically going to a number. But this is one of those rare cases where, actually it's not rare, it just like is a case where this limit actually goes to infinity or negative infinity, one of those two, which we can sort of like try to determine right now. Yeah. And so how I know that is because you kind of rather than like plugging in 1 specifically right here, you actually more want to plug in like numbers very, 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 very close to 1, or whatever this limit is going to. So like if it's approaching from the right, that means like a number just barely bigger than 1. If it's a number from the left, it'll be a number just smaller than 1. Yeah. So if we do that instead, let's think about what that might look like. So if we try to plug in a number really, really, really close to 1, but just barely bigger than it, that might look like a 1.0000001, right? And then over here, it'll be like 1 minus 1.000001, right? Does that make sense? So it's this number that's barely bigger than 1, both of these places where the x is, and then but 1 is subtracting that right here, right? Okay. So if we try to like figure this out, and this is sort of keeps going. So like imagine there are like more zeros in between the 0 and 1. And by more, I mean like infinite, right? Like it just keeps going. So if I were to do that again, what would I find in this bottom, on the bottom here? Can you see that okay? Yeah. So if you think about it, for this denominator, think about it for this denominator, you'll have like this 1, right? So that's okay, that's just 1. And then you subtract from 1 a number just slightly bigger than 1. So what that means is that we'll take, okay, you have your 1, and then you get rid of 1, so then you're at 0. But then you have to get rid of just a bit more, just like barely a little bit more. So that would increase, that would end up as a negative 0.00000 ... 1, because you do like 1 and then just something a little bit bigger than that, right? Okay. So what we're looking at right here is that we're looking at a number that's bigger than 1, or bigger than this one, that's negative, and is being divided by an infinitely small number, right? So if you have like a huge number on the top, like really big, and then on the top, on the bottom, you have like a really small number. So I'm talking like 56 quadrillion divided by like 2. Like that's like, but like even more of a difference in that. Then you know that that top part is sort of like going to be bigger than the bottom part, right? And because of that, as it's as like these sort of like go closer and closer to 1, and because of that, since this is sort of bigger than this, after you do the division, it actually goes to infinity. And because this bottom is negative, it goes to negative infinity. Now, I don't know if we've really covered this in class yet, but it's something I want you to be like aware of, and to just think about it as like, okay, like just very free, like edge cases. So like, again, like we have a 1, and then we're subtracting a number just barely bigger than 1. Then over here, it's you keep it the same, and then because it's like 1.0000001 divided by negative 0.00001. And I can actually I can like do it on my calculator right here. I do 1 point, a ton of zeros, like a lot of zeros, divided by point. Okay, 1. Yeah, I get like 100 million, right? And but like that keeps going on more, and then like the number itself is going to keep getting better. Okay, does that make sense at all? Yeah. Okay. So let's think about the limit from the left side then. Okay. So what would we do first? Like where would we kind of start figuring out this one? Like what would we sort of like plug in? So yeah, exactly. So it'd be 0.9999, etc. Yeah. Okay. So we do 0.99999 ... Okay. Over 1 minus 0.99999 ... Okay, cool. All right. So if we did this again, so if we simplified this a little bit more, maybe that 0.99 over 0.0. So right here we have this number that's just barely smaller than 1, And then on the bottom, we have 1 minus that number that's just barely smaller than 1. So because we're subtracting a number barely smaller than 1 from 1, that means we're going to be left over with a number that's just barely greater than 0. So it's just barely positive, just like a little bit, just very small amount. And so we're left on the top with that like 0.9999, whatever. So it's a very similar case to right here, where you have this number that's big. It's bigger than this one, infinitesimally bigger than this one. and you divide it. And because of that, like this is like, you could say this is the same as like 999,999,999 or something. And this is like 0.000, like something really, really small. And like that can go into this 0.9999 a lot of times. So much so that it becomes an infinite amount of times. And then we can say that this limit goes to infinity. And if you graph this equation, I don't know if you can see it there. Since we know that there's going to be a 0 at 1, so let's have 1. Because if you plug in 1, if you just plug in directly 1, you actually don't have a value there because it becomes undefined, right? So if you come from the right, we found that it's negative infinity, so it'll be more like this. Then from the left, it's positive infinity. So it'll be something like that, right? I'm like very, very sure that's how it works. I can actually just go to Desmos real quick and just like make sure. Right here. Let me like share my screen on this computer. Okay. Can you guys see this? So if I do like x over 1 minus x. Yeah, exactly what I showed. Cool. Hopefully you see this. Awesome. Okay. Cool. All right. So that's like pretty much one of the only like times you'll actually ever see like that kind of thing. But I definitely just wanted to like sort of throw that out there, make sure you guys have like recognized it. Kind of important. I'm not sure if you'll see it on the exam because he hasn't really talked about these kind of one-sided limits, but definitely something to keep in consideration. Yeah. Okay, cool. Do you have any questions about like this kind of plugging in? I know it's weird. I know it's like kind of fringe casey. They'll do more with it when you get into like asymptotes and plugging in, like when you do limits to infinity, x goes to infinity, things like that. But that's not until like the next week or two, I don't think. Cool. So I wanted to go over a question that someone asked me yesterday in our session that ended up relating to the intermediate value theorem, and I don't think he recognized that at first. So I'm gonna erase this if that's cool with you guys, because I want some more space to sort of work with. So you guys know what like the intermediate value theorem is? So like what's it about? Like what's the point of it? What does it tell us? At all? It's cool if you like.
I have no idea what that is, if I'm being completely honest.
Okay, that's fine. I think we covered it maybe once very, very quickly in lecture. Miles, do you know it all, or is your mic still not working? You know, like a little bit? Okay, cool. Well, good thing I'm going to cover it because Bradshaw literally told me in an email to to make sure I let you guys know what it is. Okay, cool. So I'm actually just going to write out exactly what I have in my notes for this, and then just sort of explain it a little bit. Yeah. It's actually not too bad of a concept. I think it's kind of just like, oh, that's like common sense. You know, why I don't understand like why we need a theorem for that. And that's a good point. It is sort of common sense, but in math we sort of always need to like define everything. So let's say I have like a graph like this. This x, y, arrows, works. And then I choose like a point A anywhere on the x-axis. So say A is right here, and then B is over here. So these are just some random constants. It doesn't really matter where they are. So I'm going to define a function f of x to go from this point, which is f of a to this point f of b. Actually, I'm going to do that in blue. So basically what that means is that, like, okay, so if I plug b into my function, which I'm about to draw, it's going to look like this. That. Yeah, and then and here. That's what it's going to look like. So, oh wait, okay, wait. I need to redraw this. Sorry, I misread something. Okay, so this is b. This is b. Sorry. Okay. Then f of b is down here. This is why I'm not a professor yet, guys. I cannot draw things for my life. Yeah, that's fine. Cool. Okay. Sorry, this looks awful. Okay, draw. So, right here, I have 2 points on the x-axis, A and B, and then also 2 points on the y-axis, f of A and f of B, which are basically like, okay, so for this function, f of x, if I plug A in for x, I'll get it right here. If I plug B in for x, I'll get it right here. Yeah? Okay. So, another thing that I want to mention is that you can see sort of that this function is continuous from this point A to this point B, right? So it's continuous cont from A to B. Yeah. Awesome. So let me just like choose a random value y of 0. So whenever we use like x of 0 or y of 0, they're basically just like random points somewhere within like something that we're just using as an example. I could call it any variable, but like y of 0 is basically like, okay, it's like some like value for y. Okay. So say this one right here, this is gonna be my y of 0. Yeah. So how should I say this? Basically, the intermediate value theorem states that if there's a function f of x for which that is continuous between 2 points A and B, yeah, any point, any value y of 0, or like y 0, so like y sub 0, whatever you want to call it. So any point between f of b and f of a on the y-axis, therefore it has at least one x value. So for example, right here, just pretend that like this hits there. Therefore there must be some x value between a and b where f of x sub 0 must like equal y sub 0. Sorry, I know I explained that very poorly. I'm gonna try to like rethink my words. It basically means that like, okay, if a function is continuous from this point and this point, and then like there's a point, how should I say this? So if it's continuous from this point to this point, and that you choose a random y value in between like the y points where like plugging those points where it's continuous between like is sort of, sorry, that's so poor. How do I say this? Do you guys understand at all what I'm trying to say? Like, I know I'm explaining this very poorly.
I'm still kind of confused.
Yeah, for sure. I totally understand that. Okay. It states that, okay, if f is continuous from points from an interval a to b, and y sub 0 is any value between f of a and f of b, then there's at least going to be one value of x sub 0. So there's going to be at least one point in the x on the x-axis between these points a and b, such that f of x 0 is going to be like equal to this.
So it's basically saying like between those 2 points, like let's say it was y sub 2, then there'd be like an x sub 2.
Yeah.
Okay.
Basically. So I'm saying that like if I chose this point here to be y sub 2, then somewhere along this interval between a and b, there's going to be a value of x, so like x sub 2, that's going to correspond to that y sub 2 through the function of f of x. Does that make sense? So I'll basically say, okay, I have a y sub 2, therefore there must exist an x sub 2 such that f of x sub 2 is like good. Can you see that?
Kinda, yeah.
So if I draw this line over, I'm going to hit this point right here, right?
Mm-hmm.
And that's within that a to b interval, like right here, boom, x2. And I could do that for any value of y in between f of a up here and f of b up here, as defined by, this a b interval. Yeah.
Mm-hmm.
That's what it makes sense. It's basically like, okay, it's
More
continuous.
sense. It's just kind of a weird idea.
Yeah. I understand. Yeah, I know what you mean. It's sort of like backwards in a way, because normally you think about like, okay, I'm going to plug in an x and then get a y from it. Whereas this is saying like, okay, I have a y, therefore some x must get me to that y in this function. Yeah.
Mm-hmm.
Because the only way that wouldn't work is that if f of x wasn't defined at this point, right? Like it like jumped over it, right? Because the very important thing is that it has to be continuous from a to b. So if the function wasn't like defined, from this side on this side of like x sub 0, and then it started like right here-ish, then like obviously there wouldn't be any function right there for it to like sort of work with, right? Does that make sense?
Kinda, yeah.
Okay, here, I have an example.
Can you hear me?
Yeah.
Oh, okay. My microphone's been not working for some reason. But yeah, can you just like do an example? Because I feel like if we did an example, it would make a little bit more sense.
We'll
Yeah.
let it-
Like I remember like I'm pulling up my notes from like the reading on it, but the example that they gave was like kind of confusing, and I feel like if you gave us like a simpler example, then maybe it would make more sense.
Okay. Was it something with like cosine of x minus sine of x minus 3x?
No, it was x minus cosine of x.
Okay. I'm gonna work with, okay, because I have this one that someone showed me from like a homework, I think. And I think I can explain this to you guys pretty well. So is it cool if I try to like do that real quick?
Yeah.
Awesome. Thank you. Cool. Okay. So let's say that some function, oh, that's so weird. So I'm just trying to like think this through. Oh, I understand. Okay, let's say f of x. I get it now. Sorry. f of x equals cosine of x plus minus sine of x. Minus 3x. Okay. Can you see all those? Can you see that? Yeah. So it's talking, so the question is, according to the intermediate value theorem, cosine of x minus sine of x minus 3x equals 3 over the interval or over the interval 1 negative 1 1. Interval 1 that has a solution over this interval as sol. So when it says that has solution, it's talking about the x, right? It's talking about, okay, like between negative 1 and 1, there's going to be a value of x between that where this is true. Where like when you plug in x here, it will equal 3. Because right here, this 3 corresponds to this y2 that we have over here, right? Because that's what f of x is. Like that you could substitute like y equals f of x, right? Anytime? That makes sense? So typically when you're doing the intermediate value theorem, they're gonna be like, okay, so like here's a function, and we're not gonna say it's equal to f of x, but we're gonna say it's equal to a value here. And then it has some kind of solution over some kind of interval, which is basically like this boundary, right? This interval, a to b.
Well, will he always tell us like what the interval is, or do we have to figure that out?
No, so the intermediate value theorem is like explicitly talks about like, okay, from A to B. Yeah. Unless like for some reason there's like a domain thing where like a function is inherently like bound between two parts. They're gonna tell you what that interval is, right? Okay, so it basically says it's basically asking if this statement is true, right? And the first thing that you can think of is that like, how should I say this? Has a solution over that interval, okay. And like, so how should I say this? When you first hear like the words like, okay, intermediate value theorem, the first thing you want to think about is like continuity and interval. Like that's kind of like the definition, like that's kind of like the basis for what this theorem is like sort of founded upon, right? So the first thing to think about is look at this function. Look at this function and see what it's composed of. So if I make the claim that I know for a fact that this function is continuous over this interval of on the x-axis, how do you think I'd know that for a fact?
Is it continuous because it's a sine function?
Yeah, exactly. So it's just a bunch of different functions that have infinite domains. It has that are entirely continuous, and they're just added together, right? Because cosine of x, I could plug literally any number into x and get something, right? So it's always continuous. It's always just like going like that, right? Same with sine of x. It's just always going up and down. Whereas negative 3x is just like down and it's like infinite, right? It's just always continuous. And if you just add those kinds of functions together, if there's no break at all in any of those separate pieces of the function, then when they're all together, there's not going to be a break either, right? There's no point. There's never going to be a time when like it's not possible to plug in x to not get a value, right? Does that make sense? So you can basically always plug in any of these numbers. Because the only time you guys are going to be like dealing with like, oh, I'm not like a restriction of the domain is when you have something like 3x plus 2x squared over like over literally just x, I guess, right? Because right here, you're not allowed to, you can't plug in 0. So that would be the restriction of the domain. So if you plug this into this, then you'd have a 0 here, and then like it wouldn't even be true because it's not going to be continuous between that, right? Because it's not defined at 0. And the same thing with like square root functions, so 3x minus 2 or just x minus 2, right? If x is like 1 here, then 1 minus 2 is negative 1, and you can't You can't do a square root of a negative number, right? So that also wouldn't work. But because I can plug anything into any of those, it's good, right? So I think I've hammered that point home. So the idea is that you want to first think like, okay, are each of these individual functions continuous across this point, across this this interval that I've been given? And what does it mean? How should I say this? How should I say this? Sorry, I can't think right now. And what does it mean that there's like that you sort of have set it equal to 3, right? Because what it means is that like, we have, I don't know, like something like this. I'm not sure. And then from like -1 to 1. And then there's something 3 right here, right? Okay. Sorry, my roommate just got here with my like laptop charger. Thank you. Sorry, I did not come prepared. Like, I also need to like move these laptops, so I'm sorry if I'm gonna try to like figure out how to. Sorry. Oh, jeez. This cord is not long enough. Okay, hopefully you can still see. It's all good. Okay. How should I say this? So what this tells us is that we know for a fact that for this value of 3, there's going to be some x value solution that we know we can plug in that's between this -1 and 1, right? Does that sort of make sense? That's sort of like the application of it I'm trying to get at. Yeah. Okay. Cool. Sorry, I'm just like looking at the problem that I was like shown. I need to look into that more. It's sort of weird. So yeah, okay, sorry. I need to look at a better example of that because and just to review that. Just because I thought I had that problem and I think like this sort of like elaborate a little bit on like what it is. But I just want to like better prepare you guys because that's not really like sufficient. I think it'll be fine, but this is the sort of thing that you're sort of just gonna like run into. Yeah, okay. Okay. Do you guys have any other questions about that? Sorry, I just kind of like rambled. That was not my best moment of teaching in my life. It's cool if you don't or anything.
It's just kind of like a weird concept, so I'm kind of trying to just like wrap my head around it.
Yeah, I understand that. Again, it's basically just like if you choose a value of y between like 2 points of like 2 outputs of that function, then you're going to get an input value corresponding to that y that will point you to that y between the intervals that like between the interval that's sort of like you originally chose that y to be in between of in the first place, sort of. Yeah, I wish you could see this a little bit better because I'm sure this writing like you can't read it at all. So there's a couple different like points that you can sort of like set it up with, and then at the end, the main conclusion that you make is that okay, like something went into this that I can get out of it, sort of. Because I already know I've gotten something out of it. Therefore, I know to get like an output value, I need an input somewhere. And what this is basically saying is that, like, okay, I have an output, therefore an input value must exist between these 2 points. And the output that I chose to like have an input value that I'm trying to find in the first place is within the outputs as defined by that original interval and the x-axis. Sorry. I know that's confusing. I might try to like look up some kind of like video or something that could probably explain that way better than I can. And also, how should I say this? I think that Bradshaw will also be like holding some kind of, well, actually tomorrow in lecture, you guys should ask him to go over that, just because I know he's going to do a review tomorrow, right? So maybe that's probably a good idea. If you have like an example specifically, that would be good. And then I can review this really quickly and sort of like understand it fully and then like explain it better over the next couple of days. Because like right now it's like, I just need to like look into it again. So that's my bad. Okay. Are we good to move on from this? Or do you just need like a break from it? Or do you want me to like still like harp at you about what it means? Because I can do any of those things.
I think I'm just probably gonna ask him in class tomorrow
Yeah.
about it. But do you think you could go over like the conceptual questions that he might ask on like the test, because they're kind of similar to like the quiz things and they like trip me up?
Yeah, for sure. So like conceptual, do you mean like about continuity? Can I erase this, by the way? I think I'm gonna erase it.
Yeah, that's fine.
Do you mean about like conceptual about continuity or differentiability, or like whether or not things are like true or not, or like you have like a specific like topic or realm or section of the textbook that you're talking about, sort of, or just like in general? Because I think there's something in the practice test I sent out that that I can like go over.
I think that for like each of the concepts, like I noticed that in each of the quizzes he had examples like f of g of x, blah blah blah, and it had to like relate to that, and then he would ask questions about them like relating to each other, if that makes sense.
Oh, so like some kind of composition, you mean?
Yeah, I think I just like get confused about how to like apply some of the concepts into like a composition question.
Oh, okay. I think I understand what you mean. Do you have the practice exam that I posted pulled up at all? Check question 8 on that. Is that sort of what you're talking about?
Yeah, that's like pretty much as close as I think this practice exam will get to like what I was talking about. But yeah.
Do you want me to go over that problem specifically, or I can try to like come back another time?
Yeah, no, that's fine.
I can do this? Okay, cool. So the problem is f of x, what is it, x cubed? G of x is cosine of x. And h of x is like something. What? Root x. Okay. So given those things, you want to find g, f, h, x. Okay. So whenever you see this kind of notation, it's basically like, okay, this is a composition. And what composition basically means is that you're sort of taking one function and then plugging it in as into another function through x specifically. There's kind of a little trick that I like to do with this. Can you see this okay? I know I moved the camera a little bit. Okay, cool. So I kind of like to do a little trick like this. So I know we kind of have this sort of like O looking thing. It's like a circle. I like to think of that as like the word of. So you can rewrite this sort of as g of f. So I do it like that, like, okay, of f of h of x. Yeah. Does that make sense?
Yeah.
Okay.
Yeah.
Cool. So you kind of like do it like that way. Okay. So what this basically means is that you're kind of starting from the inside and going out. So it'll be plugging in these inside functions into the ones that's like into the one that's just the one like above it, sort of, right? Because this part is just for right here, it's just f of h of x. And then this is obviously just h of x. Okay. So we have h of x defined already up at the top. So since we already have that, let's just try to find what f of h of x is, right? So where do you think we would first like start when we're trying to find f of h of x? Or what do you think might be a good way to write it?
Would it be root x to the third?
Yeah. Yeah, I mean, yeah, that's how you do it. So I'm gonna write it out to be very explicit about sort of like understanding what this all is. So if I want to find this f of x, f of h of x, a good way to like sort of think about it is like when you have it written like this, since we know h of x is just root x, I can sort of do like f of root x, right? And then I just look at what f of x is, and then since I'm plugging in root x for x into here, I can just like put it in sort of and leave the outside function sort of alone. So to do that, I would do that, right? Can you see that at all? Can you see that? Yeah. So it's like root x to the third, or x to the 1/2 to the third, or x to the 3/2. Yeah, there's a few exponent rules. If you take like an exponent and then do it to another exponent, they multiply, right? That look good?
Yep.
Okay, so we have our f of h of x. Awesome. But now we need our g of x. G of f of h of x, right? So to write this out, I know that this is f of h of x. So I can just do a direct substitution in to right here, right? So g of x to the 3/2. Yeah. Sorry. Now let's look at what g of x is. Okay, g of x is cosine of x. So I would just take whatever this is and plug it in wherever x is up in g of x, right? So that would just be cosine of x right there, right? And to double check that I'm like not just making things up. Okay, did it like that. All right, that's this is technically answer choice C. I don't know if you're looking at it. So problem 8 would be C. Technically, we had the root x instead of the 3. That actually doesn't matter what you do. It's kind of like addition, because these can just kind of like flip flop, like the 1/2 and the 3. So it wouldn't really matter. But yeah, that's what that's looking like. Is that sort of like a showing of how that all works and stuff? Hopefully. Okay. Yeah, I'm looking at this practice exam. The end of it is like pretty good problems for conceptual stuff. Yeah. So is this good? Should I move on? Should I like go over something else? Cool. Yeah. Awesome. Okay. Cool. Do you have any other? So another thing that I know that math like exams love to have on them is where there's kind of like a table, and this is more so for like when you have like some stuff for like derivatives of functions. So there'll be like a table where it's like, okay, f of 0 is this, f of 2 is this, f of 4 is this, and then it's gonna have some big like, okay, here's like h of x is like this, and then it's gonna like ask you like, okay, what is h of 0? And then h of 0 will be h of x will be defined as like combination of like f of x and g of x in all these like convoluted ways, and it's like a very big like complex thing. So the best thing for that is literally just to like plug everything in and just try to do all the substitutions as like blatantly as possible. Just because that's like the only way sort of like really get it all like sort of worked out, right? But yeah, that's more for like later on in derivatives. Okay. So the next thing I sort of wanted to cover, I know we only have like 12 minutes left right now, is differentiability. Now, I don't know explicitly if this will be on the exam because he said that it's only covering the first 3 modules, right? The exam is only covering the first 3 modules. I don't think we touched differentiability in there. So
All he really said about differentiability was like the rule where it's like just because a function's continuous, like a function is both, it was like if a function is continuous, then it's differentiable, but if a function is differentiable, then it's not continuous. I feel like that's the most he really said about it.
Yeah.
It's the opposite.
I think it's the opposite.
Oh.
Yeah. So I can
But
sort of
yeah, I know what you're talking about.
Yeah. So that's like the right idea. So I can go over that really quickly. If that's okay. Is that like cool? Yeah, awesome. Okay. So there are 3 ways a function can fail to be differentiable. How far over can you guys see it like this? So 3 ways to fail being differentiable. I think that's how you spell it. I don't know. So the first way is that if f is not continuous at some point A, therefore it is not differentiable at some point A. So if f is not caught at A, f is not diff at A. Yeah. Could one of you guys like explain to me like why that is, or why you might think that might be the case?
Is it because it's not defined at A?
Yeah, exactly. So if it's not continuous at A, therefore there's only like what? There's only like a few ways that it can, that at a point at A can look, right? It could be like a jump, right? This is A. So if we're coming from either side, going from this side, and remember when we look at the derivative, I don't know how much we've really gotten into like what the derivative like means and everything, but the derivative of a function is basically another function to describe the slope of the original function, right? So if I have like this is x squared. Sorry, that looks awful. If I have x squared right here, the derivative of that is 2x. And so what that means is that for every point on x squared, if you take, so say I go into like A, on x squared. If I plug a into 2x, then that will give me the slope of x squared at a. Yeah. So if I go over here, I can't really determine what the slope is at either of these points because it's not continuous, right? Like it goes, okay, it's like, okay, I can kind of tell what the slope is, goes up and then goes back down. But then when it hits that normal point, it can go like all over, right? That tangent line. So it doesn't really work. And then same thing with like right here when it's not defined. Like there's not really like a specific place where it's like, okay, this is the slope at this point, right? And then there's also like your removable ones, right? So it's the same thing because we don't have a function defined, we don't have a point defined right there. Therefore, there can't be a slope at a point where that doesn't even exist. Yeah, that's what makes sense. So this is where that main idea of like, okay, if f is differentiable at a point A, therefore it has to be continuous. It has to be. But if it's continuous, that doesn't necessarily mean it's differentiable. And I'm gonna explain those two reasons why very quickly. Okay. So number 2, see that? Yeah. Sharp turn. So what's a graph of what's a function that might have a sharp turn in it?
Absolute value.
Absolute value. Fantastic. Okay. Absolute value of x. So right here, we know all this. We know the slope, right? It's just 1. Yeah, it's whatever x is. So the slope. No, sorry. The slope is just 1 for this entire point, and it keeps going here. And then once we hit this point where it just does that sharp turn, there's a infinite different like tangent lines that kind of like rotate around it, right? So it doesn't really, it's not really like defined anywhere. We don't know which one it is. So it can be any, it can be any of them. So any function that has like a sharp turn like that, you know, is like not differentiable at that specific point. It's differentiable all these other places, but not right here. Right? And when you get into like differentiability, like rules and like how to like take derivatives like the quick way, then this comes into play. But theoretically speaking, you could do the limit derivative where you do like your whole limit as what h goes to 0 of like f of x plus h plus f of x or minus f of x over h, right? It's something like this. Your limit definition of the derivative. Technically, you could do it right here, right? If you just made I guess if it goes to 0, it doesn't work. Can you do it to another number? I forget, right? Oh wait, no, it'll have to be x of. So, oh yeah. So 0 h is fine, but it would have to be at some point f of something else that's not 0 because it doesn't work there. But if you wanted to find the slope of this absolute value function at say x equals 3, then you'd plug 3 in for all of these places, and then it would like be okay. Does that sort of make sense? Yeah. But that's again, you'll literally never deal with this past this midterm because then you'll just have like the rules, and then we'll just be testing you on like the rules and stuff, which I can definitely explain much better than literally anything I've done so far. So I think once we get past this midterm, you guys will be better, and then I'll also be better. So it'll be a whole thing. Okay. 4 minutes. Sorry if that was like kind of silly. Okay. And then the third thing is vertical tangent line. Yeah. So this is when you have something that might look like this. Right? where this point right here, and like this point in the middle of this, it's straight it's straight up vertical. So if you have that vertical tangent line, well, how should I say this? The slope at that point is undefined, right? Because if we have the slope of us like a horizontal line, that's 0. The slope of that vertical line is undefined. Because then if we, if again, like this is sort of like going back to like old things, but it would be like, your y1 minus y2, so you do your y2 minus y1 over x2 minus x1, right? Since x2 and x1, if it's a vertical slope, stay the same. So say this is just like vertical tangent line. X stays the same if it's vertical. And so then it would be 0 on the bottom. And then it doesn't matter what that is, it's still going to be undefined, right? And so we can't like define the slope through a derivative function of a vertical tangent line because like its slope would be undefined, so it doesn't really work out, right? So those are 2 examples of when clearly these are continuous functions, right? Like this is continuous, that's continuous, it works out. But we can't say that it's differentiable because of these reasons. Yeah. Does that sort of like cover that up? I know it's sort of like confusing to think about it, but like you always have to think about like differentiability as like, or continuity as being a precursor to differentiability. Like a function that's differentiable must be continuous in the first place. And then it can't be these. But that's it. That's it. So I know in the practice midterm, there was like it's one of the final questions where it talks a little bit about like limits from the left and right side, and then like there's some continuity questions. Actually, the last 3 questions on the practice midterm are all great examples of how they might show you a graph or a piecewise function and ask you some questions about it. Like, okay, are these true? Are these false? And the best way that I like to go over those is when they ask you if a question is true or not. Just do your best to see like, okay, is literally there any case where what they have stated right here is false? So you just try to disprove that point, pretty much. And then once you do that, you're kind of chilling. So if they ask you, like, okay, is this statement false? Just try to think of some kind of time when it's actually true, and then you're kind of good. Yeah, so those last 3 questions are great. And then I'm probably just going to go over a bunch of the different questions like on Sunday, I think. If not, I'll probably cover a bunch of other things. And I think I'm going to have extra sessions tomorrow, an extra session tomorrow, hopefully, and then also on Saturday at some point as well. So if that works. So I think we're
Thank
done.
you so much.
I think time is up, so I'm going to stop recording. But thanks so much, guys.
Thanks.
Yeah. I'll probably post this to the YouTube and stuff like later. I don't know if that's like helpful. So, that's good. Thanks so much.
Have a good night.
Yeah, YouTube. See you.